So we want to generalize what we did with S3 in our previous video. So I've written down one of the elements of S3, which, if we remember, S3 is the symmetries of a triangle. So here's a triangle with its vertices labeled. Here's a symmetry, we're rotating it. And the way that, well, what I want to do here is I want to write this element in a way that is not going to take the sort of visual kind of positioning of the triangle into account. So if I look at this, I have the vertex 3 is where vertex 1 used to be. Vertex 1 is where vertex 2 used to be, and vertex 2 is where 3 used to be. So I can write it, if I want, something like this, where I have 1, and 1 has now taken place of 2. Vertex 2 has now taken the place of vertex 3, and vertex 3 has now taken the place of vertex 1. And so this, you could consider this a 2 by 3 matrix if you wanted to, although we're not going to do matrix multiplication with it. But this contains all of the information in that is at least algebraically contained in this symmetry of a triangle. And what we want to notice is that this this matrix here, what it gives us is a permutation, that is a function which is one-to-one and onto from the set 1, 2, 3 to the set 1, 2, 3, right? And then we have 1 goes to 2, 2 goes to 3, and 3 goes to 1. And this is what we will generalize. And so this notation right here is a more compact way of expressing this. So over here, I have written all of the elements of S3, at least if I let this element be X, all of the elements of S3 will look like this. And the way I want to generalize it is I can just, if I have, say, 4 vertices, I could write a 2 by 4 matrix, or if I had 5 vertices, 5, I could write maybe I'll make this one be 4, right? What do I have left? 4, 2, 1, 5, and 3. Let's go 3, 5. Whatever. And these are also going to give me permutations in the exact same way. And so the way we'll notate it is we'll call permutations of 3 elements members of S3. S3 being defined to be the group of permutations of the set 1, 2, and 3, right? Permutations of this set, and accordingly, S4 is permutations of the set 1 to 4, and S5 is permutations of set 1 to 5, etc., etc., etc. And we can define Sn for n, any natural number, in this way. Now we have a group that we can associate with well, for every natural number, we can have a group, which is the group of permutations of the set 1 through n, that number. Okay. Now, as you can imagine, like our notation back here with this function just really spelling everything out is very verbose. This matrix notation is a little bit less verbose, but still, you can imagine if I were talking about something in S100, that this matrix would be a little bit hard to draw. So there's actually another notation, which is the common one that is used by mathematicians for elements in Sn, which is called cycle notation. Cycle notation. And cycle notation works like this. So let me draw a random permutation. Let's see, let's make it be in S7, and I'll say 1 goes to 3, 2, 4, 1, 7, 5, 6, something like this. All right. So the way that cycle notation works is we think of this permutation in terms of its cycles. And by that, I mean this. So if I look at where 1 goes to 3. So I'll start my cycle with a 1, and then I put a 3 after it to indicate that 1 goes to 3. And then I look at where 3 goes to 4, just like this. And then 4 goes back to 1. So instead of writing a 1 here, I don't do that. Instead of doing that, I close up the cycle. So now I'll look at, so let's see, we have 2 goes to 2, 2 goes to 2, so that's just its own cycle. And then I have 5 goes to 7, so 5 goes to 7. 7 goes to 6, which goes back to 5. So 7 goes to 6, which goes back to 5. And this right here represents the cycle, or well, not the cycle, the element that is given by this matrix notation right here. And the cycle notation is compact. At least it's one line instead of two. And the other thing that's nice about cycle notation is that most of the time what mathematicians do is they will drop any cycles that have just one element in it, like this. So this element in cycle notation would be written thusly. And the advantage of this is that things can go much faster if you have less to write. So let's go back to S3 and write all of our elements in cycle notation. Okay, so for the element 1, the cycle notation is, well, sort of it's already there. We just write nothing because I have 3 cycles, each of which are 1 element long, so I don't write anything. For x, I would have 1 goes to 2, and 2 goes to 3. So 1 goes to 2, 2 goes to 3, 3 goes to 1. X squared is 1 goes to 3, which goes to 2, which goes to 1, right? 1 goes to 3, which goes to 2, which goes to 1. Here we have 1 goes to 2, which goes to 1. Here 1 and 3 are flipping with each other. Here I have 2 and 3 flipping with each other. And so that's how we would write it. And I can write these other permutations in cycle notation too. It's not all that hard. So I have 1 goes to 4, 4 goes to 2, 2 goes to 3, and 3 goes to 1. So that's that. Right here I have 1 goes to 4, which goes to 3, which goes to 1, and then 2 goes to 2, right? And 5 goes to 5, so I don't write those, right? And so now let's do a simple example. Well, why don't I multiply 2 of the cycles which are in S3 here. I'll do that up here. So let's multiply x and y. So let's do xy, which equals 1, 2, 3 times 1, 2. And so if we remember, the way that these permutations apply is what we do is first we apply the permutation that's on the right, then we go further and further to the left. So what this will look like, and this is the way we multiply permutations like this, what it'll look like is 1 will go to 2, and then we apply x, so 2 will go to 3. So 1 goes to 3. Now 3 isn't in this, it's not in this cycle, so it's not affected by this element. So I can just go straight to x. 3 ends up going to 1. And then if I look at what happens to 2, 2 goes to 1, which ends up going back to 2. So I honest to goodness have a single 2 in this cycle, which means I can erase it. And I have 1, 3, which turns out to be exactly what I have written for xy. So we've, I guess, just confirmed the truth of this equality right here.